It's no news to anybody that data sets have been getting larger over the last 2 decades. But what it's interesting is what impact it's had on machine learning research and on machine learning in practice. So if you look back 20 years ago, data sets were pretty small. And so we ended up working on a lot of very complex models to be able to get the most, squeeze the most out of that data, because we needed good accuracy with very little data. So we work on things like kernels and graphical models, so things which are pretty complex. 10 years later, the scale of data started growing tremendously. We entered an era that we call big data era. And it turns out that because it was so hard to scale machine learning algorithms to big data sets, and because there was so much data, we reverted back to simpler algorithms, to simpler days, and using things like logistic regression, matrix factorization to address the machine learning problem. And there was even a lot of discussion of what impact that has on machine learning approaches. And there was this pre-seminal paper that talked about the unreasonable effectiveness of big data sets. And what it basically says is, if you have a massive data set, you can use a very simple approach like a linear classifier or logistic regression and beat a fancy approach like a graphical model, because the graphical model could only handle smaller data sets. So in bigger data sets, simpler approaches can do extremely well. Well, since then, a lot of things have changed. Our data has gotten even bigger, and our ambitions have gotten bigger. We want to be able to deal with even more accurate models on this even larger data. And so we're forced to come up with new kinds of algorithms that can scale up complex models to huge data sets to get really amazing accuracy. And this is where things like parallelisms, using GPUs, using big computer clusters, and the type of technique that we're going to talk about today are going to be helpful for us to deal with complex models. So things like boosted decision trees, tensor factorization, deep learning. Deep learning requires tremendous amount of computation time to get the amazing accuracy it gets. And going back to 20 years ago, people were building this massive graphical models because they have new techniques to scale them in parallel and in distributed settings to be able to get even more accuracy with bigger data sets. So the summary of the story is that machine learning has evolved over the last few years to first go back to its simpler roots to be able to deal with large data sets, but today to come up with new algorithms that can scale complex models to massive data sets. That's where we are today. So we're back to the same framework we'll be discussing the whole course, where we're taking some training data, we're extracting some features, we're building some machine learning model, but the machine learning algorithm that we're going to use is a small modification of gradient descent, just tiny change, but it will allow us to scale to much bigger data sets and often perform really well. This modification is called stochastic gradient, and it does something extremely simple. What it does is take your massive data set and your current parameters WT, and when you're computing the gradient, instead of looking at all the data, because you don't need to look at everything, it just looks at small subset of the data. So it just has a bit of the data, and then updates the parameter to the coefficients to WT plus 1, and then it looks a little bit more data, and then updates the coefficients to WT plus 2, then it looks at a little bit more data and updates to WT plus 3, and then looks a little bit more data and updates the coefficients to WT plus 4. And so instead of making a massive pass over the data set before making a coefficient update, here we're just looking at little bits of data and updating coefficients in a kind of interlead fashion. This small change is going to really change everything for us and allow us to scale to much bigger data sets, as we'll see today.